Hi, we're talking about Faraday's and Lenz's law, so I've got another example here for you. There's a loop inside a magnetic field, which is constant, the magnetic field that is, at 50 um, milliwebers per square meter in the x direction. So I've shown that the red arrows are, should be parallel to the x-axis there. And inside this magnetic field is this loop and DC of the loop. So segment, not DC, the direct current, but segment DC of the loop cuts the flux line. So this is the terminology we use, cuts the flux lines at the frequency of 50 hertz. So this thing is rotating around the z-axis, and it's actually dz that's kind of, giving it the torque there around the z-axis. So we're saying that DC is cutting the magnetic field at a frequency of 50 hertz, so 50 cycles per second. And the loop lies in the YZ plane. So you can imagine that as this thing rotates, it's going to pass through the YZ plane at time t equals 0. So that's kind of where it starts, in the YZ plane. And so we're going to find the induced EMF, electromotive force, at t equals 1 millisecond, and then also part B, the induced current, and then at a different time, t equals 3 milliseconds. So before we even get to how to solve this thing, why would there be an induced current and voltage in this loop? Well, according to Faraday's law, there's an induced EMF or current if the flux changes through the loop. So the flux can change if the magnetic field changes, but here we have constant magnetic field. Or if the size or the area of the loop changes, so that's not the case here either. It's 3 centimeters by 4 centimeters. Or if the angle, because there's a dot product involved, if the angle of the loop that the loop makes with the magnetic field lines, if the angle changes, so that's what's happening here. This thing is rotating. Okay, so then we're going to have an induced EMF. All right, so let's find that angle actually. So the angle theta between B, magnetic field, and S, the normal to this loop, that angle, because we start at YZ in the YZ plane, then that angle is simply omega times t. So this is kind of the crux of the problem. Let's try to convince ourselves of this. So when t equals 0, we're saying the angle is 0. Well, that's the case because t equals 0, this thing is in the YZ plane. So the surface, the surface vector would point down the x-axis, which is exactly the direction of B. So that would make an angle of 0, and then the angle rotates, linearly with time. So that's why this is the case. Theta is equal to omega times t, and we're given the frequency in hertz. So we're going to just kind of transform this to 2 pi f t, like that. Omega is 2 pi f. So now omega is in radians per second, f is in cycles per second, or hertz. So now the flux at any time, okay, so I'll say psi of t, okay, remember we had this integral here, not a closed, but of b dot ds, like that. Okay, and here's the dot product. So we've got the angle, right? And so this just turns out to be the magnitude of b times the magnitude of s times the cosine of that angle. Nice, right? So we can do that. Now, Faraday's law with Lenz's law says that the induced EMF is the negative is Lenz's contribution, d psi dt. All right, so we take a derivative now of this thing, right? And cosine, when I take the derivative of cosine, I get negative sign, so I'll cancel with this negative. And then from the chain rule, I need a 2 pi f being multiplied here. So let me do that. So I get 2 pi f, again, the negatives cancel, b times s, then sine of 2 pi ft. And so then if I want, this is part A, by the way. I didn't mention that, but yeah, this is part A. If I want the induced EMF at t equals 1 millisecond, right? So I need to plug in 1 millisecond into the t here, so that's no big deal. So I get the voltage, I'll just write V equals 2 pi times then the hertz frequency 50, and B I have to be careful about. B is 50 times 10 to the minus third. So why is it 10 to the minus third? Because this is in milliwebers per square meter. And then the surface area, I also need to be careful if I'm not used to, you know, centimeters. We're going with centimeters. This is 3 times 4 is 12, and then times 10 to the minus 4. 10 to the minus 4 meters, because this centimeter is 10 to the minus 2 meters, and this centimeter is 10 to the minus 2 meters, and so multiplying 10 to the minus 4 meters there. And then I have sine of, and so I have, again, 2 pi times f times t, so 2 times f makes 100, and t is 1 millisecond, so that makes 0.1, so this makes 0.1 pi. I'm just going to write 0.1 pi there. And so if I do that calculation, I find that up to 3 significant digits, I get 5.82 millivolts. Nice. All right. B. So I want to find the induced current at t equals 3 milliseconds. Well, I have the voltage as a function of time. That's this thing. So now let me get the voltage as at 3 milliseconds. So I'll just write at t equals 3 milliseconds, right? The voltage is 2 pi times 50 times 50 times 10 to the minus third times 12 times 10 to the minus 4 sine of, what do we have there? We have 0.3 now pi. So you can check my work on that if you want, but I'm pretty sure that's 0.3 pi. All right, and then if I take that and if I divide by the resistance there, we're saying maybe there's a resistor there, but maybe it's just the resistance of the wire. So if I divide that by 0.1 ohms, this is in volts, this is in ohms, then I get the current, right? Ohm's law, good old Ohm's law. And so according to my calculations there, and I'll let you plug that into your calculator, I get 152 milliamps out of this thing. Nice. Okay, so that's the answer. And before I push stop here on my recording device, I just want to point out that this is an example of an AC generator, believe it or not. So what we've got here is this this coil that's rotating around in a magnetic field, and then that coil produces an AC voltage, a sinusoidal voltage. We've got it right there. V of t is equal to 2 pi f bs sine, right? It's a sinusoid. So this is an AC generator, and what we need, though, we need something to, what is turning that loop? We need something to turn that loop. And so, you could have a crank, like a human could be cranking this thing around, which would generate AC power. It could be energy harvested from gasoline could push this coil in the magnetic field, or you could boil water, and the steam would push the blades of a turbine, and the turbine would spin, and then you have this, again, this rotational movement in a magnetic field, and that would also generate AC power.